In this video, we're going to look at quantifying electrostatic energy. What I mean by that is understanding the potential energy due to the interactions of a positive and negative charge. Just to remind ourselves, opposite charges attract and like charges repel. The way we can express that mathematically is through this relationship here, summarizing Coulomb's law, where E is the potential energy of the interaction, and that is proportional to the charge of object 1 multiplied by the charge of object 2, all divided by r, or the distance between them. So let's use this equation and think about some examples of two particles interacting with each other and assess the size of their interaction. We'll start with a +1 charged particle and a -1 charged particle separated by this distance here. So I have a +1 particle and a -1 particle. Now let's compare that to the interactions between a +1 particle and then a -2 particle, and they're at the same distance or the same radius between them. I'd like to write the words big and small here to identify the magnitude of the potential energy of the interaction between these two. So take a few seconds, maybe pause the video and think about where should I write big and where should I write small. So looking at our Coulomb's law equation over here, Q1 and Q2 are both 1 in this top case divided by a radius, compared to 1 times 2, so a larger number. So we end up with this is a big interaction and this is a small interaction. Another way to think about that is a +1 and a -2 charge will be more strongly attracted to each other than a +1 and a -1 if they have the same radius. That was comparing the charge. Let's do another example below and compare the radius. So here we have a +1 particle and a -1. Essentially the same scenarios up here, but let's compare it to this. Here I've increased the radius for the second example down here. So take a few minutes, maybe pause the video and think about which of these will have a stronger attraction and which will have a smaller attraction. If you said that this is a large attraction, a big attraction because the radius is small, and that is a small number in the denominator, which makes this a larger number, you're correct. That would make this small. So what we've learned over here is that as the difference in the charge, or the charge of the particles, increases, the energy of their interaction also increases. What we learned in this example down here is that as the radius increases between the charges, the interaction potential energy decreases. Let's think about what a graph of Coulomb's law would look like. Here I've plotted the potential energy of interaction as a function of the radius between the two charges. Let's do this for, as the cases are over here, where they're oppositely charged particles that we're going to separate at given radius values. To start our thought experiment, what would be the interaction of a positive and a negative charge at infinite distance from each other? At infinite distance, they're too far away or don't interact with each other in any substantial way. And so their interaction, their potential energy due to interaction, their electrostatic potential should be 0. So at infinite r, the potential energy of interaction should be 0. As we take the positive and negative charge and bring them closer together, that should be a stabilizing interaction because opposite charges attract, and that should lower the total energy of the system. So as we decrease r here, the total energy of the system should lower, and we end up with a graph that looks like this. This is Coulomb's law, or the graphical form of it. What this plot is showing us is that this positive charge and a negative charge next to each other is more stable than a negative charge and a positive charge infinitely separated at some infinite distance. That's what this plot is telling us. As we separate a positive charge and a negative charge infinitely far away from each other, they have no potential energy of interaction. They're so far away they don't experience each other. We set that as 0. As the two charges get closer and closer, the total energy lowers and we stabilize the system. Coulomb's law can be used to rationalize several observations in chemistry. The one I'm going to discuss right now is the melting points of inorganic salts. So I've written sodium fluoride, sodium chloride, and sodium bromide here. We'll start with these three. Notice that these salts are comprised of a cation and an anion that are interacting because they're positive and negative charges. Here we have an expression that tells us the strength of that interaction, so how tightly together they are held. As we go from sodium fluoride to sodium chloride to sodium bromide, what's changing is the radius between the two charges. Notice that they're all +1 or -1 charges, but we're changing the radius. So one way we can assess how strongly held together these cations and anions are is looking at the melting point of these solids. In order to melt sodium fluoride, you would have to provide enough thermal energy that thermal energy could kind of overcome the energy of the interaction or liberate those two ions so they could translate or move relative to each other. So the hotter you have to get the salt to melt it, the higher the interactions between the cations. The colder the melting point of the salt, the less energy is required or the less tightly those ions are held together. So let's look at sodium fluoride, sodium chloride, and sodium bromide and compare their melting points. Sodium fluoride has a melting point of 993 degrees Celsius. Sodium chloride is 810 and sodium bromide is 747. What we see is that as the radius increases, the temperature required or the energy required to rip those two ions apart and allow them to move freely, that is decreasing because the strength of this interaction decreases as the radius between them increases. That's for a series of 1+ and 1- ions. Let's look at a 2+ and a 2- ion. We see the same trend for magnesium oxide, calcium oxide, and strontium oxide. Their melting points are all in Celsius. Notice that we see the same trend where as the radius increases, the melting point decreases because the two ions are held together less tightly. Another interesting observation is comparing the +1 cations, or the +1 charged ions with the 2+. Here we've increased the Q values. So the charge is not just 1 and 1, it's 2 and 2. That has a dramatic increase, or results in a dramatic increase in the strength of that Coulombic interaction.